to you, Hugo. You will tell us about conformal predictive systems and how to calibrate those.
All right, I think you need to stop your screen sharing. There we go. All right, thank you. So let's see. All right, thank you for this opportunity. It's great to be part of COPA for the first time. Yeah, as Klaus said, I'm an industrial PhD student from Stena Line, and also part of KDH, where my supervisor is Henrik Boström. And yeah, so I'm going to talk to you a little bit about this work that we've done. And the title is Evaluating Different Approaches to Calibrating Conformal Predictive Systems. And before I start, I also want to mention that this is partially funded by WASP, which is an initiative to increase the competence of AI and autonomous system within Sweden. All right. Let's see. All right, so the outline of the talk is I'll give a brief introduction and some background, set the context of what we've done. And then I'll go on to talk about the study that we've done and the work that we have done and some conclusions that have come out of it. All right, so to begin, yesterday we heard some nice tutorials on conformal regression and conformal predictive distributions, which tackle the same kind of problem. So in the conformal regression case, we get this output, which is this interval. Here's an example of an interval we could get. And in the conformal predictive distribution case, we get this distribution Q, which is this commutative distribution function here. And we could essentially get an interval from this as well, as we heard yesterday, here chosen around the median, and which would generate a similar output as this. However, with this additional information, it could be beneficial in the context of decision making. The work that we have done is essentially to try some methods that have worked well to improve the performance in conformal regression and apply them in this new setting of conformal predictive distributions and evaluated their performance. All right. So just a little bit more background. We heard the nice tutorial on conformal predictive distributions yesterday, but I'll talk a little bit again about them and give you some more details and background if you missed it. Otherwise, here's a little bit of a repetition. All right, so
it's okay. I mean,
sorry, no. All right. I'll talk, or rather, split conformal predictive systems, which we have applied here. So the idea is you have your data, you split it into a training set and a calibration set, and then use this training set to train some arbitrary model, and then use this model in together with the calibration set to generate this predictive distribution for new instances. So there's this trade-off that we talked a little bit about yesterday as well, of how you do the split between training and calibration, and which I'll get back to a little bit later. So if you take a little bit closer look at the actual algorithm, we have our training set, which we train our model, where Z contains an object and the label, so X and Y, and we have our calibration set, and a new unseen object X here. So the idea is we generate these CI by the condition of which you can see here, where A is the conformity measure defined as here. But as we heard yesterday, there are other ways of defining this. but this is what we've used, where y is the label and y hat is a prediction from our trained model. So this together then defines CI, which you can see here, where sigma hat is the quality estimation of our prediction, where a lower sigma hat would be a more confident or better prediction. And we see this relationship here where we divide by the quality estimation of this prediction here from the calibration set. So we get 1C from each instance in the calibration set. And I'll get back to that. It's just a detail, but I'll get back to that later as well. And then what you do after this is, well, we sort these C and then CIs, and we return the predictive distribution. I'm not going to go into detail on how that is done. I'll leave that to anyone who's interested. There's nice papers on this. So when it comes to evaluating, there are several options. And what we've used and what we've seen used earlier is this CRPS, which is the continuous rank probability score, which is defined here, where F is the output from the SCPS. So essentially this blue line here, and we want to compare that to the optimal distribution, which would be a step function located at the true label. So here are two examples where we can see this output and the optimal, and we can see that this here would be the one to the right would be better, and when we evaluate or calculate the area between these two, we'd see that this is closer to 0, which would be the optimal score, which is would be the perfect prediction. So this is what we've used to evaluate the performance later on. I said that we could train some arbitrary model, and what we've seen from earlier work in regression conformal regression is the use of random forests, which is an ensemble of random trees. And what's quite nice about them is it allows us to use all the data for training and then use these out-of-bag predictions for calibration. So in a sense, it's a more efficient way of using the data, and also eliminates a choice of one hyperparameter. So that is one thing that we're taking from earlier work. And then the second thing is this notion of quality estimation, where so the baseline would be like no quality estimation, with sigma hat would be 1. And then what has worked earlier as well is using this variance. So when we have this random forest, we get predictions from each tree in the forest. And if the variance is high in those predictions, we can assume that the quality is low, and that it's something that would be hard to predict. Whereas if they agree with each other, we would assume that it would be an easier thing to predict. The second quality estimation method would be this is k nearest neighbors, where we assume that objects which are located close to each other are equally difficult to, equally difficult to predict. And then you see this beta in red, which is added just to avoid division by 0. Okay, so on to the actual study that we have done. So what we've done is we've taken these methods and applied them to 33 publicly available data sets, ranging from 500 to 10,000 instances, and between 2 and 15 attributes each. So nothing huge, but a significant amount of data sets. And then what we did is we set aside 30% of the data for each data set for testing. And then we split the remaining data into a training set and calibration set, where we vary the sizes. So with a ratio from 1 to 9, all the way to 9 to 1. So we'd start out by using 10% for training and 90% for calibration. And then we adjust that. So we'd use 90% for training and 10% for calibration in the end. And we'd also compare this to using the OOB method, where we'd train the random forest on all the data and then use these out-of-bag predictions for calibration. We repeated this for each quality estimation method, and then also repeated it 10 times with a new random split each time. And for all these experiments, we had the hyperparameters fixed, so they were the same for all different ratios of the split, and also for all the data sets, we'd keep them the same. So the results are presented here, where they're divided by, or split into these 3 graphs, which represent the different quality estimation methods. And each box represents one split. So at the far left is where we use 10% of the data for training. And the one second to the right is where we'd use 90% for training and 10% for calibration. And the one all the way to the right is when we used all the data for training and the out-of-bag predictions for calibration. And as you can see, they are very similar, which is perhaps as expected. But the overall trend is that the more data we use, the better the underlying model will be, and the better the performance of the SCPS will be. Even though there's quite a large amount of variance, and there's a big spread in the results. So we went ahead and actually tried to evaluate this. So we did a Ferryman test, and then the menu test, where the output is here. So up here you see the rank of the different methods, and the line is drawn at the average rank of that method. And the critical difference is shown here. So anything which is separated by more than this distance, we can throw away or we can reject the null hypothesis. And those that are connected, we cannot do that. So here you see that OOB method is actually, we can't really, we can say that it's differs from using 70% of the data, as these are not connected. So it follows this nice pattern where the rank actually follows the amount of data used for training. And they're all, yeah, as you can see, they're similar as well. So one nice result is that the OOB method actually ranks better here more often than not, which is quite nice. So if we want to compare these different quality estimation methods, we looked at the results from the out-of-bag method, and here's where we can see that there was an improvement in using either the nearest neighbor or the variance approach to estimating the quality compared to not estimating it at all and just having sigma hat equal to 1. So some conclusions, which I've essentially already mentioned, is that we've seen that there's a statistically significant improvement of using either the KNN or the variance method for approximating the quality of the estimation of the predictions, and that the OOB method is competitive with the most efficient way of splitting the data, but you get the benefit that you don't have to actually decide where to split it. Right, and some future work is we could, as we heard yesterday, another way of utilizing all the data is this cross-conformal predictive system where we'd which as well. But you split up the data and you predict using all of it. Another interesting topic would be evaluating the cost, computational cost of these methods, and also other methods of estimating the quality. And finally, some alternative metric to evaluating this in the actual decision-making context, as the CRPS does not necessarily tell us that much about the actual gains while actually making these, using these in the decision-making context. All right, I think that was all. So thank you for your time, and thank you for your attention.